Good morning, everyone. Oh, sorry. 251 confirms we're okay. Good morning, everyone. We're running a little bit late, so I'm short introduction. This is Łukasz Langa. He's talking about Coroutines, async IO framework in Python, and please give a big hand and applause to Łukasz.
Good morning, everyone. This is Thinking in Coroutines. My name is Łukasz Langa. I'm from the internet. You can find me in lots of places. In my free time, I'm helping Facebook run Python. Specifically, our mission for 2016 is get as many projects as possible on Python 3. We're doing pretty well. You can check how far along are we on our booth. I invite you to do that. Specifically, it's very popular at Facebook because Facebook loves async. There's a lot of things about asynchronous programming that just clicks with our minds for some reason. As you can see, the PHP variant that we're using is both typed faster and has async await. The C++ libraries that we're using to actually use as much CPU power as we have on our servers are also asynchronous in their nature. So is the RocksDB database layer that we also open sourced. So it sort of clicks with people at Facebook. They understand what it means. They understand why it's cool. But why? What does async mean for a programmer? So the easiest example is two variants of the same thing. We want to serve a response to a user requesting a web page. If we are able to fan out the requests to data sources, the response time is going to arrive sooner. So the latency is going to be better for the user. Everybody is happy. One of the things that I learned at Facebook is that it's the latency that drives the experience, not necessarily the time that it takes to complete an operation. So responsiveness is an important thing, also in UI, on mobile especially. On Python, we didn't have a great story about this, and very often people would just say, come on, like you can just spawn threads, it's gonna be awesome. In fact, it's far from awesome. The problems with programming with threads is that it's very, very hard to see the global state of your program. So not only is it hard to debug problems, it's also hard and complex to think about shared state. And obviously, we need locks. And speaking of locks, this also means that your threaded application might not behave as well as you would hope. The reason for it is obviously the global interpreter lock, which we still have until Larry actually does the galectomy that he just started and announced on the Language Summit. So, I have my hopes up. But currently, the state is this. This is an actual slide from an internal talk I have given about a global interpreter lock problem. We were observing that the blue thread operations are just executed increasingly rarely, and we didn't know why. It wasn't that they were actually doing more work or we had anything that we were blocked on, but for some reason, basically, we had some CPU leak. That was like the strangest thing ever, right? And what it actually turned out to be is that a red thread that was absolutely uninvolved with anything interesting, just set up by somebody to just do some logging of what is happening in the application, had a bug in it and just grew a collection over which it was repeatedly iterating on, which means it spent increasing amounts of time doing the same thing. And because of the global interpreter lock, everybody else had less time to do their actual work. So my talk here is basically to say that you don't need all this. You can use async IO, and that solves some of the problems. Actually, this is not a new problem, and this is not a new solution. Back in early 2000s, before Guido was even in the United States, and before we had pip 8, there was a project started by Glyph called Twisted, and Twisted was, at the heart of it, the same thing. But it was only after Greg Ewing added yield from to the language where suddenly it became apparent that we can have a really nice syntax to express what Twisted has been doing for all those years. Twisted was, at the time, sort of like PyPy is now. Everybody was talking about it, but people were really afraid to, actually take the leap and start using it. So the hope was that with better syntax, with a simpler way of thinking about it, we might actually be able to at least start writing simple programs in it. So since yield from, Guido has been really excited about adding this functionality to Python. And with Glyph's help, we arrived at async IO. So what is it? This is it. That's async IO in its very core. It is an event loop that calls callbacks. That's the most important slide in this talk. So really internalize that there's no magic, no complex things about async IO. The real thing that you need to understand is there is one event loop calling callbacks. What this means is this is a framework that can maximize the use of a single thread. We can't achieve inherently any parallelism with it. It is more for concurrency if we get to coroutines. But this is basically what it does. But this sounds magical. So let me actually dive inside the code that does it to show you that it's true. When we use async IO, we would do this thing. We would just say async IO get event loop, which gets the event loop for the current thread, and we say run forever. And if you actually do this, what happens internally is we are actually running a loop. That's the code of async IO right there. You can check it. It's open source, so I invite you to do that. But that example was a little annoying because it was just running nothing forever. So what does the loop call? What it calls is whatever you want, right? Like if we have any simple function that we would like to invoke, you can just tell the loop, like, please call it soon. The terminology calling soon comes from the fact that it might already have something that it is running currently. So as soon as you're free, please call the thing. We're calling 3 anythings with different arguments on that very slide. And we are calling later, at least after 2 seconds, a call to loop stop. So this is what actually happens. Everybody is happy. And it looks like, yeah, we achieved pretty much with a little code. So this is awesome. And as I was saying, this is exactly what it is executed on the event loop. A loop calling callbacks. No magic here. Obviously, the call to stop the loop after 2 seconds isn't busy looping, waiting for the 2 seconds. Actually, the loop uses a selector provided by your operating system to be smart about what callback should be called next. It's not a first in, first out loop. But doesn't really matter, right? That's a technical detail. The thing is, it just executes callbacks one after the other. So that sounds all great, but what if any of those callbacks were really slow? As I told you, it's just one thread. It's very simple. If any of those callbacks is slow, everything else coming after it is going to be slow. We can simulate it very easily by calling some operation that is going to just wait for a long time. That might have been a URL call. That might have been a database call, like anything of the sort. If we do this, then actually what we're going to see, executing the same code here, that everything else is waiting increasingly long and long and long, basically breaking the assumption that async IO helps us with concurrency in any way. Fortunately, async IO is helpful in the regard that if you tell it Python async IO debug equals 1 when you run your program, it will yell at you for having callbacks that are very slow to run. So at least we can be warned about a situation like this. That's bad. How can we solve it? How can we split work in a way where we are still executing this great amount of work, but in a way where we are not stopping anything else from being executed in the meantime? Well, obviously, the answer is coroutines. So instead of just creating a plain old function like we were in that previous example, what we're doing instead is we're creating a coroutine function. So basically we're saying async def, and instead of just assuming some operation is going to be slow, we are explicitly awaiting on it. One distinction that I like to make is this. When we're saying coroutine function, we're saying this is the function that we have defined that creates coroutines. A coroutine is already an instantiated call to a coroutine function. The reason why it's important is that that coroutine has a state, and it's going to take a while until it's complete. So whenever I say coroutine function, I mean the thing that we put in the code. Whenever I say coroutine, we mean the thing that's already instantiated. By the way, async IO sleep is a coroutine function, and its instantiation is already a coroutine, right? So this is it. How can we invoke coroutines with async IO? It's also easy. We just create tasks on loops, basically saying, please just execute this asynchronously, right? Create a task, and it's going to execute pretty well. If we do this, if we execute this code, we're back in concurrent land. Everybody is happy. We can go home, right? Specifically, what happens when we create a task is really async IO is going to create an instance of a class called task. So let's look inside, like how does this work? It's actually pretty easy. Tasks instantiate a few boring things, hence the ellipsis, but what it does at the end of its init method is it says, oh, an even loop, by the way, like please call soon one step of me, right? Just one. So what does it mean it has steps? What does it mean tasks have steps? A step might be one draw from my generator, because coroutines are based on generators, but that also might mean we already have a result, in which case we're just going to set the result on ourselves, or maybe there was an exception, so we're going to set an exception on ourselves. If not, we're just going to keep on drawing. But how do we do this? We're going to do this by saying, and by the way, I'm done now. Call me soon. So you can actually imagine that the execution in practice looks like this. We're just calling steps on all the coroutines that we have, one after the other, assuming that each of them is going to take a little time. Hence, we're actually maximizing the usage of a single thread. We're not going to wait on external I/O, but instead, we're going to keep our CPUs busy. So that's the model on which async I/O is built, having that trampoline of the tasks, just schedule symbol steps one after the other. But everybody lies, and I did lie to you too. There is one single thing that we forgot to do in our primitive example. Specifically, when I said, please call later, after 2 seconds, just stop the loop or whatnot, there's a little conflict between the coroutines that are already scheduled to be executed that are going to take more than 2 seconds, and our will to just stop the loop after 2 seconds. Fortunately, as I said, async IO is friendly to the programmer that just comes to async IO for the first time and doesn't really expect those situations to happen. If you use Python async IO debug, what's going to happen is it's going to tell you, hey, I'm closing the loop, but there is still work to do. What are we doing? So instead, maybe there is a way to say to the loop, like, please execute this for as long as it takes until it completes. And actually there is, and it's called exactly as you would expect, run until complete. That's true for a single coroutine, but what if we have many of them? And this is where the composability of coroutines comes in. Async IO provides many of them, and one of them is wait. You can create multiple tasks and tell the loop, please wait on all of them. This is how you would express this. Run until complete, we're now actually going to execute everything as you would expect. No lies here anymore. This is how it runs. So that's all great. But very often, we would like those coroutines to actually return a thing for us, right? And the example didn't really have this, right, before. But returning, as you would expect in blocking programming from top to bottom, works exactly simple, right? You just return a thing. If you have many tasks, all of the results are stored on the consecutive tasks object. So you can actually print them out. If we do this, you can see that we're actually executing the functions at first, and then we're gathering the results and printing out the results, in which case we're actually seeing, yes, some of the coroutines actually took pretty long to execute, but concurrently, we were able to start them all sort of at the same time. You understand, it's not in parallel, but it is by means of steps, which means it's pretty fast anyhow. If you only have one coroutine, the result can be simply taken right from run until complete. Same thing is true for exception handling. It's done exactly as if you would expect it. So if there's any exceptions, you can get to them by looking at the task's exception method. In this case, if we do this, we're going to see there is an exception type error, async IO sleep. Can't really tell how many seconds we want to sleep here. If we wouldn't want this exception to bubble up to our code somewhere else, but just to handle it internally in a coroutine, you would do it exactly as you expected already, knowing Python. You just wrap it on try except, and it does the right thing. In which case, no longer any type errors, it does the correct thing. So just to summarize this, and I mean, really, you now understand async IO, you can just go forth and, spread the gospel. From the blocking world, you invoke coroutines by either creating tasks on the loop and saying, hey, when you're running, just these are the things that you have to handle. Or you can simply say to the loop, I'm going to wait as long as it takes, run until complete. If you're inside a coroutine, again, you can create tasks. So you can say, I don't care when this is going to be executed, but just handle it. Or you can await, which means I'm going to wait as long as it takes and only continue my execution afterwards. This is really important because what it does is it makes all the switch points in your applications explicit. What it means is you can really reason about the shared state, knowing that in between await calls, nobody else is going to modify your shared state. But any await call might actually execute some different coroutine that might touch your shared state. This is much easier to reason about than a threading situation where everything is implicit. So that's the summary. The good thing about async IO is that there's a lot of included for you already. You can find all sorts of goodies in the docs already. So obviously, you can create connections that supports SSL as well, supports IPv6. We use it, so I know. There's TCP, UDP, Unix sockets, you name it. You can do this. You can also write clients with it just as easily. Again, it supports SSL. It supports UDP by reusing the same datagram endpoint. You can watch file descriptors, which is sort of the same thing, but for local dealing with changes. You can also invoke subprocesses. So these days, I find myself using async IO even if I don't do any networking, because just fanning out 100 of subprocesses is much easier with async IO than doing the same thing with the blocking subprocess model. So yes, this is it. And I was obviously making fun of logs and whatnot and saying, hey, with async IO, we can mostly get away with it. But if you really want deadlocks, you can still have them, right? You can still use those sorts of primitives. Obviously, I'm kidding. Sometimes they are needed. But before you get and try to use them, there's queues. Queues solve a lot of problems really nicely. So maybe this is actually a thing that you would like to use instead. This is what async IO provides. Obviously, you would be like, hey, where's my Django? There's no Django, but there's AO HTTP, which is pretty high level, actually, achieves a lot. So I recommend you looking at the documentation of it. It is actually pretty powerful. If you want a database, Postgres is there. MySQL is there. Actually, it's pretty awesome because it also supports the core API of SQL Alchemy. Obviously, not the ORM, because SQL Alchemy does things implicitly for you, and that doesn't work with the summary of us being really explicit about switch points, right? But the core, session handling and whatnot, it's the same API. If you want speed, then you can also have UV loops. UV loop is a new implementation of the event loop. You can just drop in the reference implementation and have it run at least twice as fast in prod. So async IO is pretty popular these days. There's a lot of things happening, so I recommend you look at it. But if you really want speed, you will inevitably find yourself dealing with already existing blocking APIs, and that makes you really sad because you can't do anything about it. Or can you? Yes, you can. There is a concept of executors in async.io, which basically means if we really have a terrible function coming from a third-party library, and we can't do anything about it, it was just implemented to just wait forever for something, we can just say, hey, I'm going to use a pool of threads and just go forth and run those slow things in those threads. For stuff like, sleeping, I/O with networking and whatnot, threads actually deal pretty well in Python. So you're going to see that this thing might be slower than using the async.io equivalent, but it's pretty fast too. So executors are nice. But as I said, the GIL is a thing. So if there is a CPU-intensive computation that you're doing, I would recommend you use the process pool executor instead. So async.io provides both, right? Thread pools are easier. Process pools are more robust, but you pay the price for picking and unpicking arguments to your process pool. So these are basically the good and bad sides of using either. Now, let me spend a few minutes on, sort of like how this is already used in production. So at Facebook, we are already 100,000 lines of code in, services that are on async.io, and growing daily. I'm pretty sure, by the end of the year, like that number is going to be meaningless. But this is actually from this morning, so you're the first to hear about this. Instagram is already pretty heavily invested in async.io as well. And again, we hope to be even better at the end of the year. Facebook uses Thrift very heavily internally. If you want suddenly to create clients and servers that are async.io enabled, you can do this like this. You just create a new namespace, and the Thrift compiler is going to do this, the correct thing. When it does it, you can just import your service and then start implementing your methods that are going to create responses for you, which is pretty easy. If you want to create a connection, you're using the exact thing that you would expect. You just create a server factory, and then you just create connections if you are on the client side. If you already have a connection, then you simply await on calls to the service that you're using. There's no magic here. You simply do the same thing as you would do in the blocking world, just prepend it with async.io. Same thing with calling subprocesses. We do it quite often. The API is pretty obvious here. What I very often like to point out to people is this thing. You should be letting know that your subprocesses should die with the parent. You do it like this. It's just a few magic lines in C types, but actually it tells the kernel, if you're using Linux, hey, if the parent dies, the children die with it. That's useful for production. Speaking of signal handling, obviously async.io supports setting signal handlers for a lot of things. Use it. So actually using async.io for quite a while now. I think it's going to be a year in 2 weeks since we deployed our first service on async.io. Let me tell you this, just use Python 3.5. It is much nicer to use with async.io and much nicer in general. So don't bother with 3.3, don't bother with 3.4. It's more complicated for you, and the syntax is horrific. And there's less opportunities for nice debugging. Garbage collection specifically is better. So that's one of the recommendations. The other recommendation is obvious, right? Everybody knows it. Nobody does it, at least enough. But really, with async.io, suddenly you realize that my threaded application that had this massive state and I didn't know what it's doing, suddenly you just have a few coroutines and you can just tell to the loop, just execute this guy. And at the end of that execution, you can check, hey, are there any other coroutines that end up being there, for some reason? So it's much easier to write a unit test for async.io than there would be for a threaded application. You can mock out coroutines easily. You can just tell to the loop, just run this one thing, until complete. So there's just no excuse. For some reason, I find that very often people would be terrified about the prospect of opening a new empty file and writing class, whatever test case. For some reason, that's considered, a massive psychological block. But it only takes a minute. There's no excuse. Do it. Setup debugging, as I said, asyncio is very, very friendly, explaining, what you're doing wrong if you let it. So a few things that you can do. Setup logging, if you need it, is very verbose, but you can do that. Set up the GC debugging, in which case you're going to see like, hey, I did something horribly wrong, and suddenly I have a lot of uncollectible items. And at the end, you can just set the loop to debug, which is the equivalent of Python asyncio debug equals 1, in which case it's going to start telling you all those things about, coroutines being left when you're shutting down and stuff like this. Yeah, so again, this sort of thing. One particular example that I found a little frustrating at first was just instantiating a coroutine function to a coroutine, but not awaiting on it really. So again, asyncio is really friendly. It's going to tell you, hey, you had instantiated some coroutines and never awaited on them. Like, is that OK? It's not, but you're going to know about this. So again, coroutines are based internally on generators. You don't have to know about this now, but they are. So stop using stop iteration. This is wrong. This is going to cause trouble for you. But in Python 3, as I said, there's many nice things about it. You can just return from a generator. It's awesome. Do it. That does the right thing. I like to prefer process pool executors, even though they have like inherent cost to start with. But at least they're known, and there's no surprises with the GIL. Those GIL surprises are the worst, because it takes a while to debug those. I hope that I convinced you to just read the docs and read the source, because it's pretty clear. There is a reason why Guido named asyncio a reference implementation. So do it. One last thought. In Python 3.4, when asyncio was introduced, you had coroutines expressed as a decorator, and you had to use yield from. No longer. Now you have this nice syntax. But you still might experience some code that is using coroutines and yield from. OK. I used images. My name is Łukasz Langa. I was thinking in coroutines. Thank you very much.
Yes, thank you, Lucas. We have no time for Q&A on this session, but Lucas said you just go and talk to him if you have any questions. And the next session is going to start at 11:30 sharp. Thank you, and thank you again, Lucas.
Sure.